Hello everybody, welcome to my YouTube channel. Today I'm gonna talk about kinematic simulation. So this series of YouTube video, I have already covered first three topics, which are OpenPose setup, camera calibration, and 3D reconstruction. If you haven't watched those videos, or please watch them. I highly recommend you to watch them because I assume that you have already watched those three videos, and sometimes it's tough for you to understand what I'm talking about without knowledge I have covered in previous videos. So I will just skip those slides and directly jump into the kinematic simulation. So in this video, I will cover 4 breakpoints. First point, convert pose estimation data into TLC file. And next, I will use the LSTM model to estimate joint position trajectories and additional marker trajectories. And next, scale OpenSim model and run inverse kinematics in OpenSim. So I was inspired by OpenCap with this kinematic simulation. So OpenCap is a web application. You can capture your motions and reconstruct 3D and do kinematic and kinetic simulations afterwards. This is a really nice application. If you haven't watched any tutorials, there are a bunch of videos on YouTube, and if you just go to the website, you can just type OpenCap and you can see the actual product. So just like simple explanation how to use it. So you need to have 2 iOS devices looking at you, and you will perform some type of motion like a squat, jump, or running, walking, anything. And afterwards, in the web cloud computing, they will calculate or extract the data using OpenPose and reconstruct the data. And if you go further, you can do kinematic and the kinetic simulations afterwards. And what's really good about OpenCap is it's open source, so you can access to the code written in Python, and it's a web application, so it's a little bit like a JavaScript or HTML or etc, but the main code is by Python. So basically, if you have your own 3D data already reconstructed, or like if you already have camera calibration data and the videos, you can actually modify the color a little bit, and you can just adapt based on what you need or like what you want. So in this tutorial, we already have covered like 3D reconstruction, and I already have a 3D data, so I would just need to jump into the code like from the kinematic simulation part. So that's what I'm gonna talk about, and starting from converting pose estimation data into .tlc file. So going to the first part. So what is TLC file? So TLC file is a specific format for trajectory or tracking 3D data basically. So if you just go to the OpenSim website, the file format is gonna be like this. So first 3 rows or 4 rows, it will have like a bunch of information about the data, and after that you need to sort the data into XYZ and joint by joint basically, and you will get frame number and time sequence right here. So this is the format that you have to convert from the 3D data Yeah, basically. And actually, I've never showed how the data looked like. So in the previous video, I showed you this code, how to extract the data from the JSON file, and I can show you how it looks like. So just loaded the data here, and I will just proceed the tracking, and there are two people detected in the first frame, so I will choose the first one, and it will track and model the data, separate the data into XYZ in the confidence rate. And if you look at the raw data, it will be very noisy, and it contains like a lot of zeros, so I have to clean up the data. So all those are like missing data, so I have to fill them out with linear algorithm. And do that, I will smooth the data based on the residual method I explained in the previous video. And if you just look at the data after filtering and cleaning up, so you will get like this, like nice and smooth data. So those are 2D data, and after reconstruction, I get the data right here. So I have to import the data first and clean up the box space, and like this, you can see my squat movement like this. As you saw, I was like tilting a little bit rightward. That's probably because the camera calibration wasn't accurate, probably, or maybe the accuracy of the OpenPose itself wasn't good. So those are like concerns like I had. Maybe during the process of like 3D reconstruction, I probably couldn't optimize really well. So there are many concerns why the reconstructed data is not looking good. But it's okay data. I can see the movement. So I would just decided to proceed with this data. Okay, so those are 3D data, and I have those data in this format. So like XYZ for the first joint, XYZ for the second joint, blah blah blah. So I have to turn this data into TLC format. Alright. And as I said, OpenCap is open source, so there are a bunch of really useful functions available. So for now, there is a Python code called data to TLC, so which is right here, and I just extract those two functions. So first function is just get the name of the markers, and the next one, second one here, is actually writing down or saving the TLC file from these 3D key points. So what you need basically is 3D data, and convert the 3D data in such a way to recognized by this function, and define the path and the name of the TLC file, and define the frame rate, define the rotation angles. If your data is rotated somehow, you have to define like this in the dictionary format. So z-axis 90 degrees, x-axis 180 degrees, blah blah blah, you can define. But in this tutorial, I already fixed the rotation, so I just input none or like empty dictionary right here. So this function will automatically convert the data to TLC format and save it in this path. Okay, and I get the data right here already. So TLC here. So I get this data here. So that's the first breadpoint. And second breadpoint is use a LSTM model to estimate joint trajectories and additional joint trajectories. So there are two main problems from the data from OpenPose. So first one is OpenPose doesn't track the motion. So it's like a frame by frame detection, which is okay for detection point of view. However, human movement is nice and smooth all the time, and if you have data only for like frame, and there is no relationship between frame +1 and -1, it's really tough to get the nice and smooth human movement motions. So that's the one problem. And second problem is OpenPose can only output 25 joint position, which is not enough to calculate like a rotation or like complex like a joint movement in shoulder or hip especially. So those two problems from the data from OpenPose and OpenCap, they actually, this is probably the best solution to overcome those problems so far among the ways I have seen. So they trained LSTM model based on the training data with 3D data of this marker set, I think from like Beacon OptiTrack, and 3D data from OpenPose. And they train the LSTM model, so they consider the time sequence of the data. So they overcome the tracking problem, and they also solve the number of marker problems. So this is just like one optimized solution in my opinion. Of course, like if you just have like detection data frame by frame, you can just smooth the data, like you can just like filter the data, for example. But you have to like take a look at the data, and you have to define cutoff frequency if you use like a butterworth filter, or like there are like a lot of parameters you can configure, and sometimes it's very tough to define like which is the like a best configuration for the filtering. And if you do it for one model or another model, it's really tedious, and it's not consistent. However, if you just like dump the data into the LSTM model and you get the solution, then it's really useful. It's fast and it's consistent, and it's a nice and so far best solution, I would say. And since LSTM model argument additional markers, like there's like 2 markers around the elbow and I think 4 markers on the hip, you can calculate like a rotation, like a pelvis rotation, arm rotation. Of course, like you can calculate flexion and extension, which are not possible from the data from OpenPose itself. So that's why this LSTM model solution so far the best. I've never seen this like solution, and I think it's the best way in my opinion. And thankfully, those models are available also. So you just need to modify the code a little bit, and just need to extract the model information, and you just dump the the data, 3D data into the model, and you will get prediction or like estimation. And I will show you the Python code right here. So basically, you will use the function from the util argumenter.py. So what you need basically is tracking data you have created from the previous section right here. In the past, so this is output, yeah. So this is output folder, and this is output name for the file, and this is the TLC file we created in the previous section right here. And I have to define my body weight, body height, and this is the path for the model. So I saved up all the models right here. So marker, argumenter, and LSTM, and there are couple of versions you can use. In the default version is number 2 right here. So I just stick to it. Of course, like if you wanna go for the other models, like there are text file which describes the details of each model, so you can like switch around and play around based on what you need and what you have actually. And yeah, you can calculate offset as well. So basically, this argument TLC function, you can just take a look at the code right here. I'm not gonna go to the details, but basically just like load the data, reformat, normalize the data, and you will impose mean and standard deviation, and you will here, I think in the carriers, you will import the model and dump the data and predict the data by model right here, and you denormalize the data, and you will save the data in TLC format right here again. So after that, you will get argumented data like this, like a TLC file right here. So I think TLC data is readable in the notepad. So if you just let's take a look at the TLC data first. So like this, it's only like a x by z data, and each joint positions from the OpenPose like this. And if you just go to the argumented data afterwards, you will of course get XYZ data, but probably also you will get additional markers which are coming after, so anything study is estimated marker position. So C7 is not defined from the OpenPose, so it's estimated from the model. So shoulder, ASIS, right side, left side, PSIS, etc, etc. So you get additional markers right here, which is very nice. And then after that, I'm just going back to the presentation slide. Scale the OpenSim model based on my body weight, body height, and the static pose. So for the static pose, you can take a look at the documentation in OpenCap. You have to have nice and good static pose, but I forgot to do it. So I just chose to have like a static pose in the first like 1 second of the squat. So basically like standing pose with the hand on the hip. So it's not really good static pose like defined by OpenCap documentation, but that's what I get, and that's the like best static pose like I had from the video so far in the like a squat video. So I just decided to use that like a 1 second like short clip of me like standing before the squat as a static pose. So just jump into the Python code again, and what you need those functions from the util OpenSim. I think at this point you have to download the OpenSim. So basically you just go to the OpenSim website and download the OpenSim. Afterwards you will create an environment like an Anaconda environment, and you can download the OpenSim packages. Then you can use the function of the OpenPose. So to scale the OpenSim model based on my anthropometry, you have to first tracking data you just created in the previous step, and you will need to import the environment of the scaling. Those XML file is also available from the OpenCap repository, so you just need to download it. And here OpenSim model, so those models also available from the OpenCap repository, so you just need to download it. And body mass, body height, and the model you can output, and the time range for scaling. So as I said, I just decided like first couple frames for static pose for scaling, and the scale model name, and I mean like you can put whatever you want right here, and you just run this function with the variables I defined here, and it will save the scaled model. So if you just go to the model folder right here, you will get scaled model like like this one. I have a bunch of them, I don't know why, but yeah, OpenSim adjusted contacts, yeah, right here, and scaled, adjusted, scaled. So there are some models automatically saved. And then after you scale the model, you can run the inverse kinematics. So of course there's a function for it, don't worry about it. So run ik2. So that's a function you can use from this Python file, but basically you just import the OpenSim like a scaled OpenSim model, and you will use the functions from the OpenSim, and the OpenSim functions will calculate inverse kinematics based on the TLC file we have created in the previous section, and the scaled model you have created right here. So after that you get nice kinematic information or kinematic data right here. So they save the data in MOT file, which is a motion file, and you can run it. You can actually visually see it in Notepad like this, right? But nice thing about MOT file is you can open it, or you can visualize it in the OpenSim. So if you just open the OpenSim, and you can open the model. Just go back to the model here, and the scaled adjusted context right here. So you will get nice model right here. You can zoom in, and there are additional markers which are not from the OpenPose but estimated. And again, the scaling wasn't that good because I used the not good static pose, so the right side is a little bit sinking, yeah, and the left side is okay. But let's see. So you can load the motion. So if you just go back to the kinematics here, and you can download the MOT file. Yeah, right here. So the pose is okay, probably. But yeah, if you just play the motions, the squat is ugly, and I've never done the squat in this way. But probably this is because of the bad static pose and the bad data from the 3D reconstructed OpenPose data, right? Well, yeah, but I can see this is a squat, and I know how to improve. So having good data from the OpenPose and do the 3D reconstruction properly, and do the static pose in a good way. But yeah, so this is what you can have. Of course, you can rotate. This is my ugly squat like this. It's okay. Yeah. So this is kinematic simulation using OpenCap. I mean, like OpenSim. And hope you enjoyed this tutorial. And next video I will explain kinetic simulation. So calculating the force, ground force, and the mass activation, etc., etc. It's very cool and very nice. And yeah, of course, as always, if you have any questions, you can leave a comment, and I try to answer those questions as quickly as possible. And until then, stay tuned and see you. Bye.